write down the curvatures and so on. Discuss that. So today's lecture, as I promised yesterday, I'll say something about the geometry of locally symmetric spaces. I mean, it's of non-compact type, which means quotients of symmetric spaces of non-compact type. Okay. So main reference that I'm using for today's lecture is one of the main theorems proved in this paper by Eberlein. In 1980 in the Annals. I'll discuss one theorem in this paper. The title of this is lattices in spaces of non-positive curvature. That's the title. So this is this reference, and he uses a certain lemma called the Margulis-Gromov lemma. So for this, both these things, the main theorem, I'll basically sketch. I'll not supply all the details. I think both these things can be supplied with all for minute details in some, maybe later on some seminar or something like that. But my thing is to just give a sketch. Okay. For this, I use a certain reference. And that reference is this monograph called Gromov's almost flat manifolds. And this is by it's what I'm doing is a very small part from this reference. The second reference is for this lemma that's going to be used in understanding the structure. Okay, so with this setup, so yesterday we were talking about symmetric spaces of non-compact type. And I said that they are the most famous examples of manifolds of simply connected or header-mod manifolds, what are called header-mod manifolds. That means simply connected manifolds with non-positive sectional curvature. Okay, and so if you have such a manifold of dimension m, let me just denote, usually the simply connected with by m tilde, the dimension n. I recalled yesterday that Cartan header-mod implies, that's why they are actually called header-mod manifolds. Cartan header-mod theorem implies that diffeomorphic to Rn, the n-dimensional space. Okay. So that's where I more or less left off yesterday. And so symmetric spaces are examples of that. You could think of, in particular, the hyperbolic n space. It's the most classic example. Yeah. Real hyperbolic. Okay, and you keep that picture in mind, and in particular I might be writing pictures from the upper half plane. Okay, All right. So now when we want to talk about locally symmetric spaces, so they are locally symmetric in the sense that around each point in the symmetric space you had the geodesic symmetry map, which is a global isometry. And in the locally symmetric space, you would want that each point should have a neighborhood in which the geodesic symmetry map is isometry. That's the neighborhood. And if you have a neighborhood, it takes the geodesic symmetry takes a neighborhood to itself, because we marked yesterday that the distance from the point is a radial isometry. Distance from the point of the geodesic is maintained. So if you have a neighborhood of some radius r, let's say, it takes geodesic symmetry takes it to r sufficiently small. It takes it to that neighborhood, and that we demand that that's an isometry. So that's what locally symmetric. This basically takes care of locally symmetric for all point P. And the way you can kind of construct locally symmetric spaces are by constructing quotients of symmetric spaces by discrete subgroups of isometries, so that the metric descends down. Okay, and so Pralay in the afternoon talked about what are called lattices, and I mentioned that these symmetric spaces they're homogeneous and they have this description that you can write it as groups of isometries modulo the isotropy subgroup, which is compact. And one wants to look at lattices with discrete subgroups in G, and the quotients are these. And he will talk a little bit more. So to construct that there exist such quotients in higher dimensions is the work is done using arithmetic. In dimension 2, uniformization tells you that various surfaces have constant curvature and so on. But in higher dimensions, the construction is using arithmetic. So there exist such things, and part of it will be discussed by Prof. Okay, so which means when we talk about locally symmetric spaces, we know that there exist such things. So I assume that there exist locally symmetric spaces. There exist such quotients by discrete subgroups. So there are plenty actually. I'll just write locally symmetric spaces. When we talk about these, there are two kinds of locally symmetric spaces. When you take the quotient, the non-positive curvature, or some of the arguments that I say, I just assume negative curvature for convenience, it's much easier. So there are two kinds of quotients. One is that quotient is compact, and another is quotient which is non-compact but still admits finite volume, a finite measure of the quotient. So compact as well as finite volume. We use the terminology finite volume to mean that non-compact but finite volume. It's also finite volume, but just use the term. Okay. So the main theorem that I would like to talk about in this paper of Eberlein basically refers to these finite volume quotients, and in some sense how does the non-compact quotient look like? So there's a nice geometric description, which is what I will sketch a proof of. Okay. So since you take quotients by groups of isometries, so let's just discuss a little bit. I'll just start here, discuss a little bit about isometries. Hadamard manifolds. I'll just look at Hadamard manifolds M tilde. For convenience, let me just look at this following curvature condition, that's negative, with sectional curvature. And assume, let's say, minus p squared less than minus a squared, 0. Okay, negatively curved. theorems, actually the main theorem that Eberlein proves, is also holds for some spaces with zero curvature also. Maybe I'll just mention sometime later. Okay, so this Cartan-Wiedemann theorem tells you that this is diffeomorphic to Rn, R open unit ball in Rn, and and one has a kind of compactification of M tilde by adjoining.
So it's a variable also, is it?
Variable. In particular, rank on locally symmetric spaces. And as I said, sometimes I can also hold zero curvature. So I'm now basically discussing a little bit more about geometry of non-positive curvature, geometry of negative curvature, of which these are specific examples. So I'm just giving you a description of that. I mean, I want to say that the negative curvature forces certain descriptions of the non-compact portions and isometries. That's what I'm trying to look at. By adjoining, so you compactify by adjoining with a certain set of points called M tilde infinity. I think many of you know that because we have had a Riemann geometry workshop. So this is the Eberlein coordinate compactification. Some people also refer to it as Gromov compactification. But I think the description is quite neatly written down in this paper. Compactification. So you write this like this. I'll say a little bit. So M tilde, as I said, since it's diffeomorphic to Rn, I'll just write it as, let's say, open unit ball. And open unit ball has this sphere, the unit sphere, Sn minus 1. And in fact, you can identify M tilde infinity topologically with the n minus 1 sphere. And these points have a description in terms of the geometry of M tilde, in the sense that each of these points is a certain equivalence class. So each point, let me call it X here, X belonging to, let me just write either M tilde infinity. I will not go into great detail about the homeomorphism, but I'll just at least mention this. Means that it is an equivalence class of what called asymptotic geodesics. I'll say what asymptoticity is. So I'll just write the picture. So you have a geodesic, since I'm talking about complete manifolds as I mentioned yesterday. So geodesics are defined for all time. Let me just look at some parameterize the geodesic by some unit. I mean, if you parameterize it by arc length, that is unit space geodesics, and suppose this is some point gamma 0. You look at gamma t for t bigger than 0. Okay, and I'll say, meaning I look at what are called geodesic rays in some sense, and I'll define it, but I can actually talk about geodesics themselves. So what is the equivalence class? What is the equivalence relation? I'll define that. Gamma 1 is asymptotic to gamma 2 if I look at gamma 1 t, I look at gamma 2 t, and I look at the distance, the Riemannian distance in M tilde between the 2 points, and I look at it for t bigger than or equal to 0. If this distance is bounded by some constant, then I say that they are asymptotic. And it's easy to check that that's an equivalence relation, and typically what you could do is, if you have a finite point meaning point in M tilde P, you could look at the unit tangent sphere S, S of P maybe. You look at the unit tangent sphere, which means you look at unit vectors based on P. And as I mentioned yesterday, each unit vector gives rise to a geodesic starting from that point in that direction, and complete means that you just look at short time. At least in this case, I look at positive time. And actually, so each vector gives rise to a geodesic, and they determine actually different points of the sphere at infinity. I'm just trying to say that given each direction, you have a geodesic, and you look at the asymptotic class of geodesics which are asymptotic to each of those, and that's roughly how you show that. It requires some proof, but show that the boundary sphere, n-1 sphere, can be identified with the points at infinity. Okay, so that thing is important, and you can actually put a topology on this adjoining sphere at infinity, such that this M tilde is dense in that, and so on, usual compactification properties. And another thing that you could do is that you could put a topology in such a way that you could extend the isometries are now defined on looking at isometries of M tilde. Isometries have a natural extension to the sphere points to infinity, because I mean you could take a point at infinity and look at it as a geodesic, and you isometries takes geodesic to geodesic, so it will take asymptotic classes or asymptotic classes, so you can extend it continuously. So the isometries extend continuously, which means isometries extend continuously as homeomorphisms. Okay, so extend continue, put such a topology. Okay, so now among the isometries of my Hadamard manifold, since we are interested in looking at discrete subgroups, so we know that this gamma, the standard covering space theory, acts on the universal cover freely and properly discontinuously. So in particular, if I take a non-identity element typically here, it acts, it has no fixed points inside. An isometry, when you extend it to the closed unit ball, it should have a fixed point, because there is homeomorphism of the closed unit ball, it should have a fixed point, and such isometries should have fixed points on the sphere at infinity. And isometries which have fixed points inside, they are called elliptic isometries, and we are interested in because we are interested in looking at these quotients by which interested in isometries that do not have fixed points inside. And I'll tell you what negative curvature forces on the property of such isometries. Okay, so given an isometry tilde, look at function d sub phi and define this function from m tilde to r, actually r plus. It takes a point P to the distance between P and P. Okay. By the way, one property of negative curvature and non-positive curvature is that some of these distance functions, this distance function for instance is convex. Convex in the sense that if I restrict to geodesics of m tilde, which means that I will have a function from R to R, it's convex function from R to R. If it happens in each geodesic, so then call this function, that's what I call this function a convex function. And distance between geodesics is also convex function. There's a convexity property, and that plays a very crucial role in many important consequences, some of which is what I'm going to describe. Okay, so I will not give the proof of convexity. Okay, so now when you look at this d5, so we can classify an isometry. We can look at an isometry with these three properties. d5 has a minimum, meaning it attains a minimum, the minimum value it can attain, and suppose the minimum value is 0. It can have a minimum value which is non-zero. It has to be bigger than or equal to 0 after all. Value, positive minimum value. Which is positive. The third one, let's say d phi has no minimum, in the sense that as the points go towards infinity, the d phi on that keeps going decreasing. It never really attains the minimum inside the manifold. So you can sort of classify isometries phi with the three properties. And naturally, if this happens, if it has a minimum 0, which means it has a fixed point, and we are interested in, that's called an elliptic isometry, and we are interested in typically those which don't have fixed points. So I'm not really looking at this. Nevertheless, I'll write elliptic isometry. And this is called a hyperbolic isometry. And this one is parabolic.
So this minimum value 0 means it has a fixed point.
Minimum has a 0, it attains its minimum, yeah. If it's 0, that means that distance between P and Phi is 0, distance function.
No, I thought that you have written we are interested in isometries.
That's right. I mean, I just wrote this, yeah. But I mean, here I'm just saying given an isometry.
Okay, given an isometry.
But yeah, you're right, I'll be basically interested in one of these. And I will tell you a little bit more further properties of these isometries. Yeah. Okay. Okay. So now I'll use this negative curvature condition that I mentioned, and if m tilde is such that it will just repeat this kind of curvature. Actually, I can just write, I can remove this, but let me just write it. Sectional curvature is negative. This can actually be removed, but nevertheless, just quickly again. Then, okay, yeah. So if an isometry is of these two kinds, namely either has a minimum value which is positive or has no minimum inside, then that's typically an analytic isometry. But it has to have fixed point on the sphere at infinity. It has to have fixed points. And this curvature condition actually forces, again by convexity and so on, then T has at most two fixed points. It cannot have more than two fixed points. I'll write an illustrative example. Fixed points, at most two fixed points. And if it has two, if phi has two fixed points, exactly to all two of them, has two fixed points, then this happens if and only if, actually, say phi is second kind hyperbolic, and next time if phi has one fixed point, happens if and only if it's parabolic. So let me just illustrate this with this example. Basically what I am saying, this conclusion is sort of easy to see in the case of real hyperbolic plane. Okay, let me just quickly illustrate that. So if you have let's take a model for this real hyperbolic plane, this upper half plane. So we know that fractional linear transformations, PSL to R, access groups of isometries.
Aravinda?
Yeah.
I have a question.
Yeah.
So this 2 and 3 says that you have d phi. Oh, d phi has. So d phi, the way you defined, if it is more than 0, it cannot have fixed boundary.
It cannot have fixed point inside.
Inside.
It can have fixed points on the boundary. Yeah.
Okay.
On the boundary, maybe. And at most two fixed points on the boundary.
In case it cannot have two fixed points inside.
Yeah. That was confusing. So that line.
On the boundary. It has to have fixed points,
Yeah.
but it's necessarily, since it doesn't have inside, it has to be on the boundary.
Yeah.
But this negative curvature forces those two. It can have only two fixed points. I'm just trying to describe that in this case. It's easy to see proof of that at most two fixed points in this case. Okay. So here, as you know, in this upper half plane mod, when we take PSL to R action on that, so which means we take this action, we look at it as complex numbers with imaginary or bigger than 0, right? Upper half plane. And we take this Z AZ plus B by CZ plus B action. And since we are interested in fixed points of this, which means that I just solve this equation. If it is fixed point, meaning I want, Z is a fixed point. If and only if these two are equal. So which means when you solve this, it's a quadratic equation. So has only at most two roots. Two roots, but what happens at most, I mean, the roots can be distinct, roots can coincide. So that's more or less like reflects the fact that the fixed points can be at most 2. But here it looks like we are actually taking a specific case, but it's a phenomenon of negative curvature actually, using convexity and so on. And you can see several things here. So that if one of the roots is complex, the other root has to be complex conjugate, and the other root has to be in the lower half plane. So it will have only one fixed point side, but we are not interested in that. If it has 2 fixed points, then it has to be, I mean, if I want to take this to be here on the real line, it could be just one particular point here, or it could even be, I mean, when we talk about infinity, right, we have this in this direction, vertical direction, or it could be 2 distinct points, I mean, one point here and one point there also. Okay. Okay. So, sort of at most 2 fixed points that you can see here. And what is the geometry of this in some sense here? So suppose it has one fixed point. Okay. For convenience, that one fixed point, let me take it to be this point infinity. Okay. So which means, since an isometry takes geodesics to geodesics, so if I take, let's say, this geodesic, and if I say that I look at an isometry which fixes only this point at infinity, essentially is this translation. It has to translate in this direction. Let's just see. Right? So the other point at infinity, here they are distinct, but here it's the same point. So in other words, since it's a translation, it keeps lines parallel to the x-axis fixed in the sense that invariant. It moves points on the lines parallel to the x-axis to itself. Or in other words, if you can take points above a certain line, it keeps it above the certain line. Okay. And these objects are all very important. They are called horocycles and horoballs, or horospheres and horoballs. Which means these are typically something above this is typically a neighborhood of this point at infinity. And those which have one fixed point, and if I just assume that one fixed point to be infinity, then it keeps these objects invariant, meaning it moves points only within them. In fact, it moves a point on a particular line to itself, and above that to again inside. And the other one, suppose I have if it fixes 2 points at infinity. So what happens is the following. So I take, let's say, 2 points, 2 fixed points here. Right, use different colors. Okay. So it fixes those 2 points, and in this particular case, you know what are the geodesics of the upper half plane? Right, this geodesic. With these endpoints and center on the real line, and that isometry does not have any fixed point inside. It has this. It has to keep this point fixed, which means basically it should not move the geodesic. All it could do is just translate on the geodesic, because it doesn't have any fixed point inside. So it translates. So in other words, it keeps this geodesic fixed invariant. So that's the typical behavior even actually in negative curvature, in the sense that if it has one fixed point at infinity, it keeps a horocycle, a horosphere, or a horoball, even in higher dimensions, invariant. And if it's a hyperbolic isometry, in the negative curvature case, given any 2 point, I mean, it keeps actually a geodesic joining some 2 points. You see 2 fixed points. Okay, you have these 2 fixed points, and negative curvature actually implies that you can actually find a geodesic between the 2 points, 2 points at infinity, and this isometry keeps that invariant. In other words, it just translates. And outside, of course, it could move by different amounts, but it translates geodesic. That's a typical behavior. Okay. So that's the. I need to go very quickly. Okay, so let's quickly isometries. And then there is one another interesting theorem I'll just write down, just because some of these theorems can be just written down from convexity and not very hard to prove, but it's beautiful to see. Maybe I'll skip that since I'm not using it. I wanted to say something about Clifford translations. Okay, why don't we just say it since I let the cat out of the bag? I mean, basically what I'm trying to say is I address the negative curvature or certain non-positive curvature. Okay, let me make two comments here. So I kept saying that for convenience I assume negative, but certain non-positive can also be, certain classes of manifolds which also have zero curvature also have this property of that it has almost two fixed points. That particular property that I am talking about is exactly what I just said, in the sense that if you have two fixed points, in general, there is no guarantee that there exists a geodesic between those 2 points. Okay? But in negative curvature you have, but also in certain manifolds of zero curvature, that particular, if given any 2 points there exists a geodesic, that's kind of known as an axiom 1 or visibility axiom. There are many manifolds which satisfy that property. So if I allow zero curvature, then I assume that given any 2 points, there exists a geodesic. Okay?
For example, in the case of flat Theorem, like R2 nodes in
Yeah,
no
exactly.
that there is
Only the diametrically opposite points you can join. Yeah, exactly. Yeah, absolutely. So, absolutely. So when you have the real R2, plain R2, that's what I want. Okay? So if you take, so here, so if I just, as I said, I'll restrict myself to the open infinite disk here. So we have these points at infinity. So each of these points is a direction. So if I take this direction and this direction, I can't quite join find geodesic. Absolutely. So that's where negative curvature is important. Or in certain specific curvature also have that property. So if they have that property, we call such a manifold with axiom 1 or visibility manifold. Okay, so if it has zero curvature, there is one more case, since I'll just write down here, not case, but I mean one more in some sense similar to this. So I'll make a definition. So if d phi is a positive constant, this function is a positive constant, which means it takes every point by a definite amount. Such a thing is called a Clifford translation. Means positive. Of course, if it's zero constant, it's identity. Positive constant. It's called a Clifford translation. And in such a case, you can actually write down what M tilde looks like. Okay, if you have a Clifford translation. So, for instance, the translations in the Euclidean plane, Euclidean space, is a Clifford translation, right? It translates by a certain amount, and that's basically essentially what a Clifford translation looks like. So, if so now let me just write. I'll just squeeze in the result here. If phi, this is the result. So people, I think basically do the golf. If phi is a Clifford translation, then this M tilde actually you can write it in as a product of, let's say, one of the, I'll just write it as a product. One of them is Euclidean factor. Another one is non-Euclidean. Okay? Euclidean factor, I mean, this can also be a product, this is a Euclidean thing. And the Clifford translation looks like really a translation in this Euclidean part, and it has to act identity on this part. Then this one, and phi is an isometry of this. So since it's a product, and this is a product, this is called Euclidean Theorem factor, and this is the complement of the Euclidean factor. I can split phi as, let's say, phi 1, phi naught comma phi 1, right? The isometries of these portions. And this one is just identity here on this one. And this is a usual Euclidean translation. And phi looks like identity comma n on m. So if d phi is a certain positive constant, then you know that the manifold has a Euclidean theorem factor on which phi acts as a usual translation, and the other portion is just identity.
So you mean that if m tilde has a Clifford translation, then m tilde must necessarily be a constant?
Yeah. That's just I wanted to. Okay. All right. Okay, so that's about isometries, and so now I'll talk about those locally symmetric spaces. The structure. Sorry, I took about 45 minutes. Okay. So now I assume that there exist such manifolds, and this is the theorem that I'm going to prove. I'll sketch the proof of this theorem. Per lines paper. Is that along the, this theorem is about finite volume quotients. Along the way, we can also see some other properties about hyperbolic isometries. But anyway, let me just write this down. So, okay, if so let m tilde such that the sectional curvature is bounded below by some constant, and I can again assume it to be negative or visibility manifold. So let me just write down. All that property I'll be using is that given any 2 point there exists geodesic. Let me just write a visibility manifold. I didn't write down, but I have just mentioned, I think many of you have seen in this workshop. The definition of a visibility manifold is that given any 2 points at infinity, there exists a geodesic. Right? And that's in some sense captures the geometry of negative curvature in that sense. It kind of gives the description of isometries. Okay? And if gamma is a discrete subgroup of the isometry group tilde, so which means I'm looking at and m is m tilde mod gamma. So which means such that let's say gamma is a discrete subgroup of this, such that is finite volume. I'm looking at non-compact finite volume. Then finitely many ends. I will describe some of the terminology that is used here. Ends or cusps. If you are familiar with the word cusps, finitely many ends. And you can even give explicit description in some sense, topological description of each of these ends. And each end is colored, Riemannian colored. I'll describe the two terms that I have introduced. Parabolic and parabolic. Each end is Riemannian colored and parabolic. And parabolic, more or less, I have indicated. It should look like in this kind of picture. If you look at quotient by ESL to Z, if you look at this H24 ESL to Z, gamma is this. So then I'll use the same picture, write down the standard fundamental domain. And that's the non-compact portion. That's the cusp. And you know that this thing is something like a cylinder, and that's typically the description here. I'll describe what it is. First, let me just say what end is. Definition of an end or a cusp. Okay. I give a topological definition. And E is a function that assigns to each end in whatever M. I mean, I'm looking at M, right? I mean, I'm saying that M has finitely many ends. And then in M is a function that assigns to each compact say K contained in M. So I look at M minus K, I have a compact set, and I'm looking at M minus K. That could have that could either be connected or it could even have something like this. So let me just write a typical picture, something like this. Let's say something like this. So it could be, this could be the compact set, and there could be more than one connected components. An end, I'll take one particular connected component. Connected. So I can say path connected or connected, both are same connected component of M minus K.
So in itself need not have to be compact.
Yeah, no, that's the thing. I'm just assuming finite volume. By finite volume, I mean non-compact thing, but finite. Okay, but such that this assignment should have some nice thing in the sense that if I move my compactness further and further, I should have some kind of containment, such that if how does it go? If L contains K, L is compact. L is compact in M and contains K, then for each compact, it gives a connected component. I didn't write, I can say E of K. So for this compact also I have E of L. And how does E of L compare with E of K? So L is bigger, and I have already taken a connected component component of this, so it should go the other way around. Yeah, EL.
So what you written? L is compact in.
If L is compact in M and contains K, then the connected component E of L should be contained in this connected component E of K. So I mean, basically we're just writing topologically this, that if I take a bigger compact set, so suppose this is EF, suppose I have taken this to be, suppose this is my compact set, and there are these two components, and I'm just looking at this component, namely let's say EFK, and if I take a bigger compact set, something like this, so this should be EFL, that should be containing EFK, all I'm saying. It just topologically describing what. So if I move further and further, the connected component is. So that's what an end is. So so if it's finite volume, it can go non-compact only in finitely many places, is what this theorem is saying. And secondly, is this clear?
So that function is real valued, or what is that function?
Subsets. I mean, it takes compact subsets to some connected components. Subsets of M. Subsets of M to subsets of M. Compact subsets of M to connected components of M. Yeah.
So then, the connected components which we are taking of outside K and outside L, it should be the same. Otherwise,
Hey, that's what. EL is containing EK.
So that means so there is a rule to select a connected component.
Yeah. Rule meaning, I mean, you select one connected component.
And for L, I could select the other connected component.
You could select other connected
But
component.
then this may not make sense, isn't it?
This is formalizing the picture that is.
I'm sorry?
Formally.
No, I don't. I mean, so to avoid what you are saying is when I am demanding this.
Okay, so
Yeah.
it should be in that way.
Yeah. That's why I'm demanding this.
So this is the defining criteria of the.
Yes. And yeah. I mean, this is part of the definition of it. One long sentence.
So cusp is also the same as.
Cusp. Yeah, exactly. Cusp or end. Yeah. That's why I just wrote end or a cusp. Yeah. I mean, I just used the word end because Riverline had used it. That's all. Yeah. It's the same as cusp.
Finite volume for cusp. End is called a cusp, is finite quality.
Sorry?
Something like an end can go like this and
Yeah.
cusp can like that.
That's right. Yeah. Okay.
You need some
End could open up is what you're saying. Is that what you're saying?
Yeah.
Yeah. I mean, this end allows that possibility. But I mean, well, what I want to say is that, okay, you want to distinguish between end and a cusp in the following sense. So here I am looking at finite volume, so it will really necessarily be a cusp. And if it's not finite volume, you could
For
still
general,
take.
yeah.
If it's not finite volume, it could open up. Instead of going cusp like that, it could just open up like a. That's also an end.
This
But I'm only looking at finite volume.
because this definition goes to topological spaces.
Correct. That's right. It's topological space. Yeah. It's topological definition. Okay. And I'll just say a few words about what it means to say parabolic and Riemannian color. Unfortunately, I'm way behind my. Anyway, as long as I convey the picture, I'll be at least happy. So, parabolic and Riemannian color, what does it mean? Let's say an end. I'll just describe an end as E. At the moment, as I said, I'm only looking in this situation, finite volume, and which means it's actually a cusp. E is said to be color, Riemannian color. It's basically it's exactly the same description. There is some compact thing, and with zero infinity, half real line. Yeah, it's said to be Riemannian color. So this is the term I'm defining with a line. If there exists neighborhood, but I never defined what a neighborhood, but anyway, a neighborhood U of E. I never defined what a neighborhood U of E is, but if it's contained in some open set, actually, I mean, I suppose neighborhood of n means, I mean, an open set which contains that. Okay. E such that okay, so, well, let me write this down. Let me not write several other things. Yeah, if neighborhood of E, a compact 4-dimension 1 submanifold, which means it's a submanifold of dimension, if manifold is of dimension n, submanifold is of dimension n minus 1. Which I write it as manifold, let's say H. There is something about, yeah, the original manifold could be smooth, but submanifold need not be smooth actually. There are level sets of certain function called the Buseman function, called the horospheres, which I just mentioned in the picture. In general, well, in the situations of symmetric spaces, these horospheres are smooth. But if you just take the general case that I am taking, variable negative curvature, not necessarily symmetric spaces, the level sets, I mean the horocycles, this function, the Buseman function is not in general smooth. In general it's C2, so the level sets will also be C2, even if the manifold is smooth. But in L, I will not write all that. What I meant to say is that there is some regularity stuff involved. So H of M and diffeomorphism. I mean, this diffeomorphism is also not smooth. It's just C1 diffeomorphism because this things is C2. So I'll just not write all those regularity things. Diffeomorphism F from H cross half real line to this neighborhood, such that if I write T for the parameter here, and let's say it's H for the point in H, such that when I look at T going to F of H comma T, that's a curve, and these are H and T. These curves are unit speed geodesics. Not only unit speed geodesics, because I'm looking at this end, these unit speed geodesics, geodesic rays.
And also you want to say
minimize the length.
H of 0 is H.
H of
Begin.
yeah, you could take that. Yes, yeah. Sorry, I'm only looking at the geodesic rays. I'll just vary T.
So I'm saying that H is a submanifold. F of H of 0 is H. You want to say that?
Yeah.
F of H0.
Yeah. So you want me to say that, yeah, F of H comma 0 to H. Start from H.
That will force H to be a subset of V, right?
Subset of
Subset of
H. I mean, it's in H. It's like this. If this is H, I take a point in H, and what I'm saying is, oh, because of the neighborhood U, right? Well, I don't need to demand this. Let me just take this away. I don't need to demand that. Yeah. I'm just looking at open neighborhood. Maybe I shouldn't say here. Yeah, you are right. I think I'll avoid this here because this is open. So thanks. I'll just take it. This, yeah. So that this edge of this end thing is somewhere inside for some point. Let me take this. Sorry, since I mentioned this is open, so I better. Thanks. So I think this. But I'm looking only in this direction. That's what. Yeah. I mean, I'm in the neighborhood. Unit speed geodesics, and this unit speed geodesics. So it intersects. I mean, edge this place. So it intersects this. Yeah, unit speed geodesics. Not only unit speed, it's unit speed minimizing geodesic. By minimizing, I mean if I look at any 2 points on the geodesic, the distance is actually the it's parameter the arc length. So it's the arc length of the geodesic. Minimizing, that's also important. Minimizing geodesics. H, minimizing geodesics. M, quotient. And these geodesics intersect. This hypersurface. For each T, I get this hypersurface, each hypersurface. Hypersurface, I've got to pay. Hypersurface means for each T, I get this level set. So it should, this geodesic should intersect this orthogonal. I'm mentioning all this so that your finite volume manifold, it has finitely many ends, and each end is like a product. The neighborhood of each end is like a product, and these geodesics are, so the ones I'm writing are these geodesics. If I take a point here, these are the geodesics. So it's a kind of a pencil of geodesics. Basically, topologically, you could compress along those geodesics. That's, I think, what you might want to use, perhaps, yeah. So that's the description. And it's parabolic. What is parabolic? Means that that particular endpoint is a parabolic response. Yeah. Yeah, all this definition is basically justifying the picture that we write. It is compact cross some interval. Is parabolic. If there exists by divergent meaning, I mean it just goes off to, I mean leaves every compact set divergent. Geodesic ray gamma that so I'm looking at these geodesics which leave compact, it means typically these parameter ones. So you can say that this geodesic kind of converges to the end. Okay, that's one could use that word. Okay, basically that enters, if you put it this way, that enters E, that converges to E. Can be expressed as, so since that's a geodesic in the quotient, it's minimizing and enters infinitely long into the cusp, it can be expressed as actually the image of a geodesic minimizing from, and write it as gamma equals to this, where gamma tilde geodesic in M tilde, such that so far I have not defined what a parabolic thing is. Gamma tilde infinity is a parabolic fixed point. Is fixed by some parabolic element. Is fixed some parabolic element. It is something related to what you were saying yesterday, existence of unipotents in finite volume lattices, not compact volume. So Eberlein uses a certain word, generalized unipotent elements, isometries, and so on. It's very similar to this. Maybe I should put it down. So the geodesic which enters the end infinitely long is actually the image of a geodesic, or at least the positive part of the geodesic coming from the universal cover, and the end point is fixed by some parabolic element. If that happens, then I call that negative parabolic element. Very similar to this picture. Okay, so let's hope to sketch the proof. Let's see. I have 20 minutes. Maybe I'll just give you the strategy and write what Margulis Gromov lemma is and so on. So let's. By the way, I mean the crux of the whole in this theorem, the most crucial ingredient is the Margulis Gromov lemma, and various other things are just broken up into sequence of some 5 or 6 lemmas, which basically come from the behavior of isometries and geodesics and so on. And you. So let me just write down in some sense what the strategy is, at least, so that you will know how the theorem is proved. I intended to do more, but strategy. Proof. Okay. First step to prove the finitely many ends is that I'll just break it into, meaning I'll just write it in some steps, and these steps can be proved by some lemmas. So there exist only finitely many distance minimizing in space geodesic rays, but I'm looking at only one half of the geodesic rays. Let's say gamma 1 to gamma sub k, starting from some point P, P is a point in M, from where there are only finitely many minimizing ones. So which means that if there are only finitely many, that's the first step in something strategy to prove. If there are only finitely many, that means that each such can actually enter into a cusp, so that basically shows that there can only be finitely many ends. Okay. And second, which means they come from gamma 1 tilde, gamma 2 tilde. So here. Okay. And then the crucial ingredient, I'll state what this lemma is. Called marvelous Prof lemma. So
It's distance minimizing diverging geodesic rays.
diverging meaning leaving compact sets. Yeah. If it's distance minimizing, then it has to diverge, no? In M. Geodesic rays. If it is distance minimizing, it has to leave all compact sets, no? In M, yeah. That was marvelous Prof lemma. I'll say what this lemma is, and perhaps what I'll actually do is, instead of sketching the proof of the theorem, I will actually, which can actually be done, maybe I'll just indicate what, one of the two, maybe marvelous Prof lemma. I'll decide. This is the most important lemma, crucial lemma. I'll say what this lemma is, but I'll first say what this lemma implies. Yeah, is used to show that each xi, which is gamma a tilde infinity. You remember these geodesic rays, finitely many, they come from some gamma tilde, because the distance minimizing, they come from some geodesic rays above. And so for each of these gamma 1 to gamma k, I have gamma 1 tilde to gamma k tilde geodesic rays coming from elliptically covered. So I can look at the point at infinity of that, and each of this, where we use marvelous Prof lemma to show that each of this is fixed by some parabolic isometry. Let's say phi sub I in gamma. For each, each meaning of for one decimal phi. Okay. 3. Again, use marvelous Prof lemma. Show that and show that. That will give you some description of what this end is like, the Riemannian colored thing. So what is this H, the compact one, which I already kind of indicated. This compact H is the level set of a Boltzmann function, I said, right? So there exists invariant horospheres. Horospheres are level sets of Boltzmann functions. Invariant horospheres means this parabolic isometry keeps that horosphere invariant, like this picture. So it's very similar to that picture. Horospheres Li at these points that are determined xi. So which means, let me just write a picture. Maybe I'll write a picture here. So this is how M tilde looks like, and suppose I have this xi, 6 point. So you have these objects, levels of Boltzmann functions called horospheres, and if you include them inside, they're called the horoballs. Yeah. So this Li, if this is xi, typically Li is this. Li at xi, such that we can write down what h is, such that horosphere based at xi. Now, among all elements of gamma, since anyway I have at least one element phi I in gamma which fixes this point, so I could look at all isometries which fix that point. So which is what I write as, let's say, gamma sub xi, which means all elements of gamma which fix xi. So this is compact. So in other words, when I go from m tilde to m, this picture, which is m tilde mod gamma, so this m, which I write here, m tilde mod gamma, if I write the picture like this ends, finitely many ends, let's say something like this. Okay, so I have these. So suppose I take one of these. So this corresponds to xi, and its compact portion is precisely the horosphere modulo the action of the stabilizer at this point, and that's compact. So you have this whole horosphere, right? I mean, for each parameter. I mean, suppose you take a geodesic going to that. So for each parameter, you look at the horospheres. Cutting this actually orthogonally. That's all this orthogonal description comes from this picture. So in the quotient, you have a Riemannian color like that. It's compact and invariant horosphere, compact, and so I suppose this is where gamma xi of all is here such that phi x is x. Okay, I mean phi xi is xi.
The L mod gamma xi corresponds to the
H. Yeah. In other words, the projection. I mean, if I take this mass as phi of Li is H. Okay, that gives all the following thing. So I have 10 minutes. So maybe I'll just state what the modulus Gromov lemma is. That's very crucial, and try to see if I can actually sketch a proof of that. Okay. So first, let me write down what the modulus Gromov lemma is. I've covered a lot of ground. That's true. Maybe. This. And I would be happy at least if I can just indicate how such a thing lemma is proved. Okay, so this is modulus Gromov lemma. This whole proof of this theorem, by the way, is broken up into something like 6 or 7 lemmas, all of which are not hard. I wouldn't say easy, but not hard. But this lemma, which is one of this, is crucial. This is a highly unclear lemma. Okay. And where was my assumption? Yeah, this is my assumption. And if let's look at dimension bigger than or equal to 2. N is the dimension bigger than or equal to 2, and b squared or whatever is given there. Yeah. There exists, depending on the dimension n and this curvature bound, there exists an epsilon. It depends on m and this b, which is the curvature bound here, b squared. Of course, know that I'm looking at not all such manifolds, but visible in manifold. That's important here. Such that this is Yeah, in the same situation, M tilde is a Hadamard manifold, which is visibility manifold, and gamma is a discrete subgroup, and so on. If let's get gamma epsilon at point phi, let's see. Okay, so let's put it this way. Let P the point P tilde as the theorem, and that is given by gamma epsilon P. So this consists of all generated by elements phi in gamma, such that d phi, the function that I wrote, when isometry phi, the d phi, the function that I wrote, point p is less than epsilon. I look at all elements of gamma which move point by most epsilon for this particular epsilon. Yeah. If you look at this, what modulus Gromov lemma says is that then gamma epsilon is almost nilpotent. It tells you what the structure of this is like. Almost nilpotent. What do I mean by almost nilpotent? It contains a nilpotent subgroup of finite index. That is, contains a nilpotent subgroup So this is a very interesting and crucial lemma. This is used to tell you how this gamma sub xi looks like, because geometrically, since I mentioned that I have finitely many ends and cusp in the finite volume looks like what I wrote here. So as you kind of go deeper into the cusp, that's where you will have point and the elements of gamma which move only by at most getting smaller and smaller epsilon. It's kind of giving you a structure of this. That's how that's where it's used. Can be made a lot more explicit in the case of lemmas and so on, which I thought I will do, but I think I just have about 4 or 5 minutes.
This is in the case of symmetric space.
Sorry?
Is it in the case of symmetric space or
You could do it in the visibility case also, visibility manifold. In that setup you could do it, yeah. I mean you could do it for case, yeah. So why don't I just I think let me spend a little bit time just to kind of say what goes
That's going to be the neighborhood of identity of the group, right?
Sorry?
That's going to be a neighborhood of identity of the isometric group.
Neighborhood of identity.
And it is consisting of only semi-simple.
Which one?
Gamma
epsilon? It's not consisting of semi-simple elements.
No, I'm saying it's a neighborhood of identity of the isometric group.
Neighborhood of identity?
No, you're taking the group generated by
Group generated
What is
by
gamma? Oh, I see. Gamma and
group generated by such isometries which move a point P by.
Gamma means what?
Sorry?
What is gamma?
Gamma is a discrete subgroup of
Gamma is as in this thing. It's a discrete subgroup such that M tilde mod gamma is finite volume.
Yes.
So does this
No.
does this say that if I take M tilde modulo gamma epsilon, then that is going to be normal?
Yeah.
Is this also
M tilde modulo gamma epsilon. Yeah. You could take that true, yeah. Yeah, it's going to be non-compact, yeah.
One does a full group, is it? Full
Which
group
one?
of finite index.
It contains a nilpotent subgroup of finite index, that's correct. Yeah. It may not be the full nilpotent, no? I mean, because it depends on which parabolic element it fixes, right? I mean, for instance, what I'm trying to say is that there are so many geodesics, right? They come from different ones here. Each of this is a parabolic one. Each of those will have its own nilpotency. Full.
For every P. This gamma epsilon P is
Gamma for 3 belong TM, yeah, I look at that, yeah, exactly. Yeah. Which means basically typically you are looking at points P which are deep in the cusp. Yeah, so I'm already time. Maybe I'll just skip that. Yeah, I think since I'm already time, I should test the patience. I meant to give a sketch of proof of this marvelous Gromov lemma. It's quite involved. Yeah, it basically involves I mean, you take a point P and you look at elements of gamma, meaning if you take an element of gamma, you take a loop in the homotopy class of that, and then in the homotopy class, you especially look at not arbitrary loop, but you look at what's called a geodesic loop based at P, which you can do, right? I mean, you unloop, you have path upstairs, but you could just join them by geodesic, and upstairs is simply connected, so they are homotopic. So what you get below is geodesic loop, and you look at geodesic loops and define what's called the Gromov product, and show that when you take a commutator of two geodesic loops, things become smaller. I mean, for each such loop, you associate certain thing called the rotation part and the translation part, and they keep reducing, and that's how you get the nilpotency. Yeah, I meant to write some pictures. Let me just stop here. I fell much short of the lemma that I wanted to write.
Can you say something about points? Can you say something about points P where this gamma epsilon is actually nilpotent?
Yeah.
Does that?
I mean, that's what points P fall into the cusp. So you would write this fundamental domain, no? I mean, you take a point P, there's something called a Dirichlet fundamental domain that you can write around the point. So in the fundamental domain, you will have certain things going like that.
So as I approach the
as you approach that particular parabolic, whatever. I mean, not this way. I mean, like this. You'll have in the fundamental domain, you will have something like that, and typically the points somewhere there are the ones I'm looking at here.
No, sir, I'm asking, can you say something about points where this gamma epsilon is actually nilpotent, not just almost nilpotent, the group in itself is nilpotent? I mean, does that happen?
That happens for sure when you go into sufficient finite covers. It is, for instance, instead of M, you go, finite cover, you can actually get nilpotent. For instance, in the complex hyperbolic case, the Heisenberg group is a two-step nilpotent.
Right, so but you won't get points in M tilde itself. You have to take certain quotients to get. The question I'm asking is, now you said that you're looking at P and M tilde.
Right.
And for for every P and M tilde, you can define this gamma epsilon P.
That's correct.
And with these assumptions, you're saying that this gamma epsilon P is always going to be almost nilpotent.
Yes.
So under what conditions will it be nilpotent? For which points P will it actually be nilpotent? Can we say something about those points? Does that?
I mean
the group.
Well, all points near that parabolic thing, no? I mean, very close to that, right?
So for all points.
Yeah, for all of those. For instance, if you have deeper inside the cusp, that's what I'm trying to say here. Look at not that picture. Look at these holospheres, right?
Yeah. So basically,
so you take horoball sufficiently
Yeah.
deep inside. Yeah.
So for something like
All
if
those
you,
points. Yeah.
if you look at the horoball with boundary Li,
Hmm.
for all points inside that horoball, it will actually be nilpotent.
But you have to go
Yeah,
sufficiently.
yeah.
Yeah.
In the first step, are there finitely many geodesic rays or finitely many asymptotic class of geodesic?
Finitely many in the, starting from the point P. In M, I'm only looking at M.
But suppose that
Starting from a point P, I'm saying, yeah. So
Yeah.
that's the point. if I fix the starting point, there won't be finitely. If I did not fix the point, then this asymptotic will not happen.
even if you fix the point, suppose
Yeah.
there is a cusp like this,
Yes.
and suppose this is some
Right.
manifold,
That's right.
and there could be more than one lots of infinitely many geodesics,
Geodesic segments you are talking about, perhaps.
geodesic segments.
But I'm only talking about geodesic rays, completely geodesic, not just segments. I mean, from this point
From
you
this
could go
point
into
to
that
end,
and then take a
and
geodesic segment. Then there'll be many. But if you want to just say geodesic, minimizing geodesic from this point, there will be finitely many is what I'm saying. Perhaps what you were saying is geodesic segments, isn't it? I mean, you said you look at the
Suppose-
compact.
Yeah. Suppose it looks like this.
Yes.
This. Now, suppose this is P.
Yes.
Now, take this 2 geodesic. Okay.
Yes.
It may continue till this.
No, that won't happen in negative curvature, right?
Oh.
I mean, from a point
Okay.
from a point there exists only one. I mean, to that pointed input there exists only one, right?
Yeah.
Yeah. Let's think about negative curvature. You can't have two asymptotic ones starting from a given point. Yes. Yeah. Okay. Thanks.